Hi, my name is Kyle Teo. I'm a student working with Professor Ovidiu Daescu at the University of Texas at Dallas. I'll be speaking about my results on the problem of finding a feasible trajectory for an articulated probe in two dimensions. So, let us begin by defining the problem. We have a two-dimensional workspace represented by a circle S. In the circle, we have n obstacles in the form of line segments and also a target point T at the center of the circle. In this problem, an articulated probe consists of two line segments AB and BC with a joint at point B. The length of segment AB can be equal to or greater than the radius of the circle S, while segment BC has a small length denoted as R. The objective of the problem is to find a feasible trajectory for the probe to reach the target point T. More specifically, a feasible trajectory must begin with a straight insertion of segment ABC into circle S. After the insertion has completed, segment BC may rotate around point B so that point C can coincide with the target point T. This process must be undertaken while avoiding the obstacles. If circle S is visible from target point T, the problem basically reduces to computing the radial visibility from T, and that can be computed in n log n time. So here on out, we're going to assume that S is not visible from T. That is, BC must rotate around B in order to reach the target point T. The problem here is mainly motivated by the applications of robotics in minimally invasive surgeries. In such applications, typically a doctor would insert a surgical probe with a rotatable end tip through an incision so that they can perform operations on some targeted tissue. In our model, the workspace S can be seen as the human body cavity. The simple articulated probe is used to model the operating instrument. Line segment obstacles are used to represent the critical structures that must be avoided during the maneuver of the probe. And point T indicates the location of the target tissue. Now, due to recent advances in 3D printing, the end tip may even be customized in size according to the specific requirements of the given patient. So previously, we have given solutions to the problem when the end segment BC is fixed in size. For n obstacle line segments, we can find a feasible trajectory in n squared log n time using n log n space. If we have polygons as obstacles, the time complexity becomes n squared plus h squared log h, where h is the number of polygons. In both cases, if we want a certain clearance from the obstacles, the space usage increases from n log n to n squared. Using our solutions, the feasible trajectories that we find are always extremal, that is, always tangent to one or two obstacles. We have also made progress in the problem when the workspace is three-dimensional, and the obstacles are now in the form of triangles. The algorithm that we have provided takes n to the power of 4 plus epsilon time and space, where epsilon is a small constant greater than 0. The feasible trajectories computed here are always isolated by at most 4 supports, which could be vertices, edges, or surfaces of the triangles. In this study, we went back to the 2D version of the problem and tried to find solutions to the following variants of the problem. First, find the minimum value of r greater than 0 such that a feasible trajectory exists, and report at least one such trajectory. Second, to find all feasible values of r. And in the third problem, to find the entire set of feasible trajectories for a given value of r. For the first two problems, we found solutions with subcubic time and space complexities. For the third problem, we found a quadratic time algorithm to compute an arrangement representing the feasible trajectory space. In this presentation, I will be focusing on the first problem, and I will briefly summarize our results on the second and third problems. So here we begin with an observation we have made in the past. First, note that the circle C in these images is the circle of radius r centered at the target point T. Now, given any feasible value of r, there is always an extremal feasible trajectory that passes through either two obstacle endpoints outside circle C, or one obstacle endpoint inside C and another one outside C. It is easy to see that this must also be true for the minimum feasible value of r. So we're going to start with such extremal feasible trajectories. Change the value of r until we reach the extremal feasible mean r trajectory. What we have found is that an extremal feasible mean r trajectory must belong to one of these 5 possible scenarios, where the extremal conditions are indicated in red. Now, if we look closely, we can see that an extremal feasible mean r trajectory is always tangent to at most 3 obstacles. So, what we have is a set of n-cubed combinatorial events. We can simply enumerate and verify them for feasibility. A trajectory is feasible if both segment AB and the circular sector BCT are free of obstacles. That can be checked by performing a ray shooting query and a circular sector emptiness query. For the specifics of the query data structures, I would kindly ask you to refer to our paper. So, the time and space complexities for both ray shooting and circular sector emptiness query problems are summarized here. The result is that we can find a feasible mean r trajectory, if one exists, in n cubed at log n time using near quadratic space. Now, the next question is, can we do better and obtain a subcubic time algorithm? The answer is yes. And we begin with another observation, which is segment AB is always tangent to 2 obstacle endpoints. So we're going to start with such extremal trajectory and perturb the value of r while maintaining those tangencies until we reach the extremal feasible trajectory with the minimum value of r. And now I'm going to go through the specifics of how to do those perturbations. We begin with a pair of obstacle endpoints, U, V. We have a trajectory with segment AB intersecting U and V, and the length of segment BC at its smallest, that is, the angle of rotation of segment BC is exactly 90 degrees. In step 1, we check to see if this trajectory is feasible. Again, just like before, we do a ray shooting query and a circular sector emptiness query for that. And briefly, for answering the circular sector emptiness query, we constructed a data structure that is based on the lower envelope of n bivariate functions. If the trajectory is feasible, then we stop because we have found a feasible mean r trajectory where segment AB intersects U and V. If the trajectory is not feasible and AB is not free from obstacles, then there is no feasible mean R trajectory such that its segment AB intersects U and V. Otherwise, we are left with knowing that the circular sector BCT is not free of obstacles, and we go to step 2. In step 2, we first check to see if BT intersects with any obstacles. This calls for a radius intersection query, which can be answered using a data structure based on a lower envelope of n univariate functions. If BT intersects an obstacle, then there is no feasible mean R trajectory where AB intersects U and V. Otherwise, we move on to step 3. In this step, we slide point B towards V, like the way it is indicated by the arrow in the picture, until the corresponding segment BC is free of obstacles. And that requires us to perform a ray shooting query to find the first location of point C in this sliding process, where point C first comes into coincidence with an obstacle line segment, and BC is free from obstacles. After that, we check to see if BT intersects any obstacles by using a radius intersection query. If it does, then there is no feasible mean R trajectory with AB intersecting U and V. Otherwise, we can go to the next step. In step 4, we slide point B further towards V until BT intersects an obstacle endpoint. And for that, we need to do what I call a radius shooting query to find the first obstacle endpoint that BT comes into contact with when sliding point B. And the query data structure that we have developed is based on the half-space decomposition scheme by Matuzak. So after that, we do a circular sector emptiness check to see if the sector BCT is empty of obstacles. If it's not, then there is no feasible mean R trajectory where AB intersects U and V. Otherwise, we go to the next step. Now in step 5 and the final step, we slide point B away from V in the opposite direction as we did before until the arc CT is tangent to an obstacle, and that requires an arc shooting query to find the first obstacle that the arc CT comes into contact with while sliding point B. For answering the query, we have to construct a data structure consisting of an upper envelope of n bivariate functions. And that's the end of step 5 as well as the perturbation procedure. And we have found the feasible mean R trajectory with AB intersects U and V. Here is a summary of the queries necessary to carry out the procedure I have just described. In this work, we have successfully addressed a number of interesting geometric query problems by using data constructs such as lower envelopes and half-space decomposition schemes. Since we have n squared possible pairs of obstacle endpoints, without using any query data structures and just simply checking against each obstacle for intersections, we can find a feasible mean R trajectory in n cubic time with linear space usage. If we use the query data structures, the time complexity improves to n to the power of 2 plus epsilon with the space usage in the same order. Now, in the second problem, to find all feasible values of R, we extend the algorithm that I have just described. Without going into details, the extension basically allows us to find all contiguous feasible subsets of R for every pair of obstacle endpoints. For example, in the pictures, the two-headed arrow indicates the feasible range of R for a given pair of obstacle endpoints U and V. Similar to problem 1, without using any query data structures, we can find all feasible values of R in n cubed time. With query data structures, the time complexity improves to n to the power of 5 halves. In the third problem, we want to find the feasible trajectory space for a given value of r. To do that, we begin by characterizing 3 different configuration spaces. First, the final configurations that are allowed by the articulated probe. Second, the forbidden final configurations, which are intersected by the obstacles. Third, the infeasible final configurations, for which the circular sector is intersected by the obstacles. And the feasible trajectory space is simply the set of all allowed final configurations, excluding those that are forbidden and infeasible. As it turns out, the characterization of these spaces are given by simple curves, where any 2 of the curves intersect at most once. As a result, the arrangement has the worst-case complexity of n squared. By using topological sweep, constructing the arrangement would take n squared time in the worst case. This result also implies by simply traversing the cells of the arrangement, we can find a feasible trajectory for a given value of r in quadratic time, an improvement of a logarithmic factor compared to our previous result. So, in summary, we have successfully developed algorithms for solving 3 variants of the trajectory planning problem. For the first 2 problems, we have given algorithms with near quadratic or subcubic time complexities. In the process of deriving the algorithms, we solved a few interesting geometric query problems by designing efficient query data structures based on lower envelopes and half-space decomposition schemes. For the third problem, we show that we can compute the feasible trajectory space for a given value of r in quadratic time. Some open questions remain. Can we improve upon the query data structures? Can we extend the solutions to the case of clearance? Can we generalize the solutions to 3 dimensions? We hope to address, if not all, some of these problems in the near future. Here is the list of references used in the presentation. Thank you for watching.